All right. Good afternoon, everyone. So in today's workshop 10, we'll be looking at colors of coordination complexes. We'll be doing a few calculations and looking at the color wheel and how ligands affect color. So we'll start off with our color wheel, and we have our primary colors present there, right? So we have red, orange, yellow, green, blue, and violet. And each of these primary colors are associated with a specific range of wavelength for light energy, right? So we have visible light, and visible light occurs between 400 and 800 nanometers. And each of these different colors are associated with a specific range. So for our violet light, we'll start off with our lowest wavelengths between 400 nanometers to 430 nanometers. And then as we go into our blue range, we'll start at 430 nanometers and go to 490 nanometers. And then for green, we'll start at 490 and go to 560 nanometers. And then for yellow, we'll go from 560 to 580 nanometers. And then for orange light, we'll start at 580, ending at 650 nanometers, right? And then our red range starts at 650 and ends around 750 nanometers, right? So those are the ranges of those are the wavelength ranges for visible light, based on the colors that we see. And when we look at our transition metal complexes, we can think about our electrochemical or spectrochemical series impacting which color that's absorbed by a transition metal complex, and also the color that we observe. So as a quick review for our spectrochemical series, if we go from our strong to weak ligands, right, we have cyanide as a strong ligand, then NO2 minus. We can also have enamine, pyridine, which is about the same as ammonia, NH3. And then as we go weaker and weaker in strength, we have EDTA. And then we can also have water as a ligand, our aqua ligand. We have our nitrito ligand that's bonded through oxygen. We have our oxalato species, and then hydroxo species. We have fluorine, our thiocyanato, FCN minus, and then we have our other halides, chlorine, bromine, and iodine, right? So that would be our electrochemical or spectrochemical series. And on the left, we have our strong field, ligands. And on the right, we have our weak field ligands. And for our strong field ligands, we'll pair that with our high spin octahedral splitting. And our weak field ligands are paired with our low spin octahedral splitting. Another thing that we can associate with our strong and weak field is that for our weaker field ligand, they'll have a longer wavelength when we think of our wavelength of visible light. And for our strong field ligands, they'll have a shorter wavelength. Right. And another thing that we want to note is that when we're looking at the colors observed for our transition metal complex, we want to remember that the observed color is complementary to the color of the one that's absorbed. So the observed color is complementary to the absorbed color. So that means if we have a transition metal complex that absorbs light, in our red wavelength, we would observe a green color for our complex, right? So that's one thing we can think about. Now let's go through some examples where we can actually calculate this value of energy for our octahedral splitting values. We can calculate this value of energy. And then also what we can do is determine what color will be absorbed, what color our complex will be, and then if we change ligands, how that affects the color that's observed, right? So if we look at chromium, our hexa-aqua chromium 3, we're saying that it absorbs light at 570 nanometers. And if we're looking at this species, we can actually start to calculate what our octahedral value is. And the calculation that we'll use for that, we'll say that our delta O, right, our octahedral splitting, will be the combination of Planck's constant times Avogadro's number times the speed of light. So all three of the values in our numerator are constants. And then in the denominator, we want the wavelength, but we want the wavelength in meters, right? So that's the formula that we'll use. And for Planck's constant, we will say that the number is 6.62 times 6.626 times 10 to the negative 34 joules seconds per ions. That's our value for H. Our value for Na, Avogadro's number, is 6.022 times 10 to the 23 ions per mole. And then that also needs to get multiplied by our value for the speed of light, which is another constant, 2.998 times 10 to the 8 meters per second. And then we'll take that entire numerator and divide it by our denominator, which will be our wavelength in units of meters. So we'll take our 570 nanometers and multiply it by, we'll get rid of the units of nanometers. We want it in units of meters, so we'll multiply it by 10 to the power of negative 9, and that will be our value in units of meters. And when we calculate that, we should get a delta O of 210 kilojoules per mole, right? So if we look at our units, we see that our units of ions cancel, our units of seconds cancel, and our units of meters, our units of meters cancel as well. So the last thing that we have, or the last units present, are joules per mole. If we take the value in joules per mole and divide by 1,000, we'll get our value in kilojoules, right? So that would be kilojoules per mole. So now we know that, or we're told that this complex absorbs light in 570 nanometer range. So if it absorbs light in 570 nanometer range, that means that we'll absorb yellow light. So yellow light is absorbed. And if we're absorbing yellow light, then we'll see or observe the complementary color. So since we're absorbing yellow light, we'll observe violet light. So complex will be violet, right? Now, what if we replace our water ligand with NH3? So let's take our molecule, Cr, H2O, and we have 6 of them. And we want to switch out our ligands from being water to being NH3. So now we have Cr, and our ammonia is a neutral ligand as well. So we have a similar complex, right? We're going from one compound to the other. In our spectrochemical series, right, we're taking, if we're comparing water to ammonia, we can see that we actually went to a stronger field ligand, right? So since we've replaced our water with a stronger field ligand, then we would expect to have a shorter wavelength. And if we get a shorter wavelength, then that means that we want to basically see a shorter wavelength for that molecule, right? And then we've answered that question. Now, what about D? If we replace water with Cl, then our molecule becomes chromium. We should still have 6 chlorines. I guess I don't need the comma brackets anymore. So we should still have 6 chlorines. Now our charges should be 3 minus, right? So now that's our new complex. And when we compare these in our spectrochemical series, we see that chlorine is a weaker field ligand, which means that we should get a weaker field effect. And since we're getting a weaker field effect, we should get a longer wavelength. And the wavelength that we're comparing is the wavelength of our complex with water. So we're saying that the wavelength would be shorter. In C, it would be shorter than 570, and in D, it would be longer than 570 nanometers.